right, so thanks for coming today. We're excited to have Arfon Smith here. Arfon was an astronomer at one point, and so I know him from his days there. And since then, he's been doing a pretty interesting career path. If any of you are familiar with some citizen science initiatives like Galaxy Zoo, where people go on the web and start identifying galaxies and helping scientists with some of the pieces that we can't automate. Arfon worked for Galaxy Zoo for a while, and since then he's been working at GitHub, doing things, lots of interesting things, some of which I'm sure we'll tell us about. So let's welcome Arfon.
Cool. Thanks, Jake. All right, hi everybody. Thank you for inviting me. It's always good to be on campus here. It's one of my favorite places to be. So today I want to talk about academia's biggest blind spot, in my opinion. And it's been pointed out to me that maybe academia has many blind spots, so maybe this is just one of them. But yeah, my career has been spent writing a lot of software in lots of different academic settings. And so I want to talk about some of that today. If anybody reads about open source generally, this is a riff on a title. There was the industry's biggest blind spot recently, a post by a lady called Nadia Egbal about how the tech scene isn't actually supporting open source development very well, and so this is my riff on her title. In case you think I'm copying her, I am. Okay, so I think for me, academia's biggest blind spot is software, and when I talk about software, I mean software that's been developed in an academic setting and probably for an academic purpose, and its status within academia and the status of people writing software. In truth, a lot of what I say today could be said about data as well. There's a lot of similarities in how we might want to treat people who produce very, very rich, useful data sets, maybe even people who work on instrumentation in astronomy, that kind of thing. But today, primarily, I'm going to focus on software. And the thing is, software is important. Like, this isn't a statement without backing. The research community says this. In about 2009, there was a big survey of a few thousand academic scientists, primarily, and more than 90% of scientists say that software is either important or extremely important to their research. And it's part of everything they do. And of course, software is kind of everywhere in modern research, but also in industry. GitHub is, hopefully some of you, maybe most of you know about GitHub. We host a lot of source code for lots of different companies and individuals. And one of the main funders of GitHub, a guy called Mark Andreessen, who wrote the Mosaic web browser originally, if people know what that is, predates Netscape. And he has this phrase, software's eating the world. And this is true. We see this in industry. I think we see this in academia. If you talk to people at John Deere who make awesome machines like this, they consider themselves software companies these days. There's actually a lot of controversy about whether you own the software on the tractor you buy. John Deere say you don't. You have a license to use it, but you can't take it and use it on another piece of hardware. That's an aside, but that gives you an idea about how they're thinking about themselves as a company. They consider themselves a software company that happens to build tractors. The same is true of Ford, the same is true of General Motors these days. And so we're hearing about...
A local stat, by the way, Boeing has 4 times as many software engineers as aeronautical engineers.
Right. And so this is, we're hearing about lots of industries being disrupted by software. Maybe Uber's a favorite example for lots of people. John Deere is a good example from a more traditional industry. I'm kind of interested in whether the same is going on in academia and what we need to do to sort of enable that. And so this is a great quote by one of the lead engineers of scikit-learn. Software turns a theoretical model into quantitative predictions. Software controls an experiment, and software extracts from raw data evidence supporting or rejecting a theory. And I think I really like this quote because I think it just kind of expresses the kind of broad range of topic areas where we see software in modern research. And I think it's this kind of importance, this role of software is only likely to increase. And I think there's a bunch of reasons that might happen. But I think giving a particular example that's relevant for this campus, you know, as you see larger facilities, this is the Next Generation Optical Survey Telescope, LSST. When you see more and more centralization around these large instruments, more and more people are using these the same tools, the same pipelines to analyze these data products. As we see sort of bigger science experiments come online, or whether it's kind of large volumes of data, this is the sort of next generation. There's always a next generation in every field, of course. This is the next generation sequencing technology. In bioinformatics, this is called a nanopore sequencer. That is a USB port that it's being plugged into. It's powered. You can just kind of pipette the sample in the top there. You know, software is playing a critical role in both the generation of these data sets, these large data sets, but also the analyses. And of course, there's theoretical examples here. I think this is the Millennium XXL simulation, the most recent, you know, simulation of the cosmos. Produced, and these, you know, these shared data sets, software is both critical, the way that these data sets are produced, and then the ongoing analyses that people do with the subsequent data sets. And Victoria Stodden, who's I think at University of Illinois these days, has this real concern about this, that we have deep intellectual contributions, part of the research product encoded in software, and yet this isn't necessarily stuff that always gets out into the literature and is reviewed. And so she comes at this from a kind of real reproducibility concern, and sort of different way to kind of present that would be, you know, certainly in very, very large data-rich environments, genomics is a good example where not necessarily the skills that people have traditionally had coming into these fields aren't necessarily on the kind of computational side. You've got this risk if you have these large instruments producing enormous amounts of data, that you turn to kind of black box methods, where your grey box methods here, where you're you know, turning a handle, pumping data into some set of tools, producing results at the end that you're publishing on, but there's very little insight into what's going on in the analysis. And so, put a different way, and this is my XKCD style plot of reproducibility, as we become more data intensive, there's this risk that as more and more of the kind of scholarly activity, and this is Victoria's kind of argument here, that as more and more of the scholarly output ends up in software, and we're not publishing that, and we're not reviewing that, then our ability to reproduce this work, or understand its kind of the full spectrum of what the researcher did, is reducing. And so lots of people get very excited about this crisis in reproducibility. Some of you will have seen this plot. Over the past decade, there's been about a tenfold increase in the number of retractions of papers, but only about a 50% increase in actually the number of papers produced. So we're, you know, and you can see the kind of breakdown of reasons there. There's actually some nice, there's a guy, one of the deputy directors at the NIH, a guy called Phil Bourne, has this challenge that he set people to try and reproduce some of their own work from, say, let's say 5 years ago. Could you go back and get the same result for a paper that you produced 5 years ago? And that's a test of whether you're being diligent about storing your work well, whether you're capturing, you know, whether you're versioning maybe your analysis scripts or your data sets. But he pointed out that his lab failed miserably at this. They couldn't reproduce their own work 5 years after they produced the initial result. They could get moderately close in some cases, but they certainly couldn't produce the same plots. They couldn't, you know, they just didn't have that. They hadn't captured the kind of provenance of their work as they were doing it. So that's a kind of interesting thought experiment to try and reproduce your own studies. And so there are a bunch of reasons for wanting potentially to kind of unpack what's going on inside you know, inside these software, inside these you know, data analysis routines, pipelines, that kind of thing. But the problem with our current kind of state of affairs is there are very few incentives for the individual researcher, if you've written anything in here, to actually spend the time and effort maybe publishing your software, sharing it with others. Very few incentives for the individual, because most of the credit that's kind of applied in research settings goes towards, you know, papers that people write about their work, not the algorithms and the data sets that were also produced. So So I want to talk for the rest of the day about some of the kind of things that I think we need to be thinking about going forward. So one thing that's, I think, usually missed, I mean, some research groups get this really, really well, and I think they get a lot of success because of this, but something I don't think we talk enough about in academia is that software can be a competitive advantage for the individual researcher and for an individual research group. And I've been lucky enough to see that a couple of times in my career, and first was actually in bioinformatics. So after being an astronomer, I went and pretended to be a bioinformatician for a year, and went to the Wellcome Trust Sanger Institute in Cambridge. This is the site where they sequenced about a third of the original human genome here. There's a joke here, something about bioinformatics buildings being much more attractive than physics ones, but I'm not sure what it is, but that is literally what it looks like. It's a really wonderful campus if you get a chance to visit. And the Human Genome Project, just to kind of revisit where the Sanger was for more than a decade, this was a multinational project. Multi-billion dollars. About 15 years took to complete 3 billion base pairs, the size of the human genome, and it cost about $3 billion. Nobody's completely sure, to be honest, but about $3 billion. It's a lot of money. And the thing that was happening at Sanger was this, the Sangers produced about 1 billion of those base pairs in that reference genome, and they had these sequences that looked, I think these are the right pictures, it's kind of hard to find them now, but they had these sequences, and it was a factory, it was a DNA sequencing factory, so they had an absolute ton of these things. I think they had about 600 of them, and all they did, they had one process, they had the same genome, they were preparing it, they were putting it into this sequencer, they were producing the data, all of their tooling, all of their processes were built around this one project. So there was an absolute metric ton of Perl. One thing most people won't tell you about the human genome is there was a shit ton of Perl written, and if anybody's ever written a lot of Perl, then the idea of 5,000 Perl modules under version control to go and look through is kind of terrifying. A really old school astronomer once told me that Perl looks like modem noise, which I don't even know what that means, but I don't think that's a good thing. Anyway, so an absolute metric ton of Perl, and I joined the Sanger. I don't know how many people have ever seen this plot. This is the cost per raw megabase of DNA, and we've got Moore's law plotted for reference here. And so I joined the Sanger right in 2007, just when it's dropping off the cliff. And that was because there'd been this change in technology. So the human genome was completed in 2004 or something, whatever. Anyway, it was they were experiencing this rapid change in the technology, and it was this. It's called I think it's still called Illumina sequencing. They changed the way in which they could sequence DNA. So they chopped up all these bits of DNA, and then they actually much shorter reads, but then they took lots of images. So they actually look like star fields. Actually, if you look at them, it's like image-based sequencing. And it was this hardware. This is one of the very, very early sequencers, and that is a username and password on that computer, by the way, in case you were in case you were wondering. But when this machine arrived, it now has very nice fancy holes, venting holes in the side of it. It had drill holes in the side of it because the hardware was so new, it was overheating. Like, they hadn't even refined the hardware, but we'd got some of the very, very first Illumina sequences. And none of those 5,000 Perl modules were ever designed to think about anything other than this very, very single, like hardware, single workflow-based model. And so the only thing that was constant for about 2 years at Sanger was continual change. Like, everything changed every day. The lab protocols were changing. They were trying to work out how to make these sequences efficient. They were suddenly wanting to sequence everything, malaria, mouse. They were looking at dog, whatever. Suddenly there were thousands and thousands of genomes they were interested in sequencing. And so we had this serious problem that none of the tools that we had were able to support this. So I was very lucky to be on this new team that was formed called the Production Software Group, and we had this charge to build tools that were completely agnostic about the kind of protocols that were being used to prepare the sample. Everything had to be available online. We had to be able to build services around all this stuff, and it had to support thousands and thousands of projects. And this is just one screenshot of this thing called SequenceScape that we built, but you can see here this particular project, and this is just one person's project, and this has already got 97 billion base pairs. You can see the volume of data that was being sequenced. So that's about 30 times more than the human genome, just on this single malarial parasite sequencing. So this was a real eye-opening experience for me to kind of see software being built for research in this way. Straight off the back of that, and Jake mentioned it at the start, I had this I feel I was very lucky to be involved very, very early on with this project called Galaxy Zoo. So I joined very, very different, lots of galaxies, lots of people, but 2 postdocs and a student. Nobody was funded to work on this project initially. And I joined after the original Galaxy Zoo project had been built. It was a website that looked a little bit like this, in fact a lot like this. And we'd built, the team had built one project and knew they wanted to build more. And so the job was, to build what became the Zooniverse and this collection of projects. And we only had 2 people. It was Chris Lintott, who was the research postdoc, and I was the engineer on the team at that time. And we knew we wanted to build more projects. So we knew we wanted to support lots of different domains. And so this is not meant to be good looking to look at. This is the decision tree that you go through in Galaxy Zoo. But we basically made this decision to invest in, this kind of shared domain model that would allow us to build things like Galaxy Zoo, but also build things like, this is the most addictive project on the internet still, I'm convinced, an animal classification project from images from the Serengeti. I encourage you to go and have a play if you haven't. It's ridiculously addictive. But we built this shared tooling. This was a project to look at MRO images from Mars. We built this tooling that could host all these projects, and it had to be, these were our kind of requirements. It had to be fast. We had lots of people using it. It had to support lots of different science projects. It had to be really highly available, as in like reliably online, because we had such a large community who used to send us emails and get very upset if they couldn't look at pictures of animals. And it also had to be cheap. Like, we didn't have much money. So this was kind of what Zooniverse was. But with all of these in mind, and we were lucky, we made some great hires, actually finding kind of reformed, or people who were happily leaving academia because they weren't very happy with their research career. But we found these people who were interested in building tools, and software became our competitive advantage as a research group. We thought we were going to build maybe 3 or 4 projects in 3 or 4 years, and we built about 30 with our tool set. But I think the problem with both of these is that both the Sanger and both Zooniverse were special cases in their own right. One is because the Sanger is funded, some of you will know about the Wellcome Trust. Henry Wellcome, I think, invented the medical first aid kit. He made a lot of money in the First World War, made like field medicine kits. And there's a great museum in London, by the way, the Wellcome Gallery. But it had thousands of staff there, hundreds of engineers on site, and there were career paths for people who were research software engineers. You started as a junior engineer, mid-grade, senior. You had some idea that there was career progression for you as an individual. And the Zooniverse, I think, was special because it was staffed by people who'd given up. Like, they had no aspirations writing papers. Didn't join because they wanted to do research. They were there because they were excited about the project and they wanted to write software. So neither of these, I think, if software is becoming increasingly important, and I believe it is, I think we need to find ways for these to not be special cases. How can we make it so that every research group, if they want to, can enable people to write the best software they possibly can, and for that to be their contribution in academia, not just papers. Because I think right now there's no particularly good reason for people to stay around if software and methods are what you particularly care about. And sorry to embarrass you, Jake, but Jake wrote this probably the best way I think I've seen it expressed in a really nice blog post, which is kind of shouting, why we should be alarmed about this. The skills required to be a successful scientific researcher are increasingly indistinguishable from the skills required to be successful in industry. And I think this is a huge risk to the academy. So the crux of it for me is that software currently isn't a creditable research output, and there's this idea of people getting on the Google bus. I managed to find a picture of one. This is what it looks like. It's got air conditioning and Wi-Fi, probably snacks as well because it's Google. But
You crop out the
Yeah, I did. Most of them were like people with banners in front of the Google bus. So yeah, this is one of the few ones that was licensed for use that didn't have people like throwing eggs at it. But anyway, that's the San Francisco thing. Anyway, put another way, Phil Bourne at the NIH, we must find a way to legitimize software as a form of scholarship. And so, hopefully this isn't incredibly boring, but I spent a lot of my time thinking about ways we might be able to fix this. So I'm going to spend the rest of the talk today talking about why it isn't, and maybe how we could address that. So this is my very kind of quick checklist. Some of these are technical reasons, some of these are cultural reasons, and so I'm going to try and talk through some of these and what possible solutions there are to some of these issues. Okay, so I think very briefly, the fixes, like if we want to make software a kind of a creditable scholarly output, then there are three broad categories of solutions, potential solutions. Some of them are self-service at the individual level, so things that you as an individual academic or an individual maybe PI or you as an individual can do to advance the cause. There are things that you can do as a small group, and group here could be research group, university department, maybe even whole research domain, like a specific subfield. And then there are things that really aren't in our control as academics, things external to universities, things that are part of the academic ecosystem that affect people's careers, but that we don't have an immediate say over how they function. And so the first one is, this is a fairly well understood kind of solution to making software creditable. You write a paper about the software. You write a software paper. This is good because it's a self-service thing, like it's on your back to write that paper. We know how to write papers. We know what that looks like. We just include a link to the software, and then when people use that software, we ask them to cite the paper about that software. So this is great. This is good. We have something to cite. We have a citable entity. We don't need to change anything about the academic ecosystem. But the problem is, like, if you've already spent a bunch of time writing software, then you've now got to spend a bunch more time writing a paper about that software. And maybe you have a tough peer review process, but it's a lot of work to write a paper. And also lots of journals don't like them, like they won't accept them. Depends on your field. So maybe you have to just put it through some random journal that doesn't actually even count in your research field when it comes to things like tenure review. And what do you do about authorship? Because if you've actually got a successful piece of software that's had a reasonable lifetime, maybe it's been through 3 or 4 releases, what happens when somebody comes along and dramatically improves the piece of software? Do you write another paper about the software? Okay, well maybe you do, and okay, so who's an author on that? Maybe you can figure that bit out, but now you have to find another journal that will accept a pretty similar paper about this piece of software that's already been published. You're going to struggle probably to get that through. And then even if you do manage to make that happen, you've now got tons of papers about basically the same piece of software, and now you've got the problem of citation dilution, which if you care about H-indexes, which lots of people do, then this is a problem if you've got all these citations spread out across a whole collection of papers. So it turns out software papers are kind of a fix, but they also kind of have some serious problems. Okay, so let's think about going beyond software paper. Then let's think about why can't we just cite software directly? Why can't we just say, let's just make it possible to write a paper and include a reference, some reference to the software directly. And this is just a slight aside here, and there are a bunch of people who've really kind of expressed this kind of convolution of things much more eloquently than I'm probably going to do today. There's an important question to hear about why do we actually cite stuff, and we need to think about that for a second. And here are some potential reasons. If you ask a librarian why you cite, they'll say to show we've done our research, and avoid plagiarism, maybe to complete the scholarly record. The one that most people answer is this one, that citation equals credit, and that is one one of the reasons that we cite, but for the system that we have built today, Jeff Builder, who is a technical lead of an organization called Crossref, who make the DOIs that are attached to most papers, says that academia has a citation fetish, and I think he's correct. Like we equate citation with credit, and that's because of the system that we exist in, but it's a serious problem that this happens because we get these cargo cults built around citation. But okay, that's just a quick aside. What might software citation look like? Well, it might look something like this: author name of the software package. For software, we probably really care about the version, so you probably want a version number in there, and then maybe some URL to the software repository. But if you look in the literature, there's actually a ton of things that just look like this, right? So my question is, like, why isn't that enough for a software citation? There are problems with that, but if you go and resolve that URL and go and look up, you can find out who the authors are, you can work out when the paper was published, you can get a rough time from that, you can probably work out roughly what version they were using. So the question of what software citation might look like is kind of the jury still out on that. But let's assume that we can do it. So yay, we can cite software natively in the literature. But actually, many journals don't let you cite software. This is a cultural thing. This is not a technical problem. You're not allowed to put software in the references. You have to put it in, the appendix or in the acknowledgements or something else. It's not allowed. The editorial process doesn't allow it to be in the references. And believe it or not, maybe people that I want to have a big row about this if anybody thinks this is a good idea. Lots of journals have citation limits. You are limited in the number of things you can cite, presumably because they're still printing on papyrus or something. But like that, you have to pick the top 20 things that you want to cite, and nothing else is allowed. So if you're thinking, well, I'd really like to cite that data I used, or that paper, or that research software I used, then it's probably not going to make the cut unless it was absolutely critical. So if there's a citation limit, software is an obvious thing to cut off. And even if you did have citations to software, the people who count citations, and this is Web of Science, Scopus, Google Scholar, don't count them. So even if they were in the literature, they wouldn't even take any notice of them. And so then if we're equating citation with credit, which for a large part of this talk we are, then that doesn't help people's careers anyway. So software citation kind of sucks as well. I get way too animated at this. I want to draw your attention to this organization called Force 11, who actually think a lot about problems like this, and I have spent about the last 9 months thinking a lot about software citation, and I would encourage you, if you are interested in this topic, to go and look at the Force 11 software citation principles. We've been doing some advocacy work. We're going to try and change this. We're going to try and encourage journals and professional societies to formalize and allow software citation in their literature. Anyway, so if you're interested in that, go and take a look. But I think everything I've talked about so far today is kind of dumb. It's I think we're trying to force something that isn't papers. This is amazing, this blog post, by the way. It's so funny. There's a video of them really going at it. It was never going to work, right? But never mind. Anyway, so I think we're trying to force software into something that was designed for papers and something. I think we're thinking kind of the wrong way about this. I think these are all hacks, and I think they're not very good. And I think the question is, like, for me, especially coming from GitHub and seeing a lot of software, there's already incredible ecosystems around software and things that these communities do well that look and feel a little bit like citation, feel a little bit like credit. And so I think there are things we can potentially learn from kind of non-academic software communities, the open source community communities especially. And the first thing I think that software does generally, like the tooling does very well, is I think it handles authorship well. There's an explicit recognition in many of the tools that people use to build, write code together, that authorship isn't a static property. And so if we look at something like scikit-learn, then, and this is on GitHub, we can see at the top right here how many people have contributed to this. But the whole tool, if you do git short log minus NSE, if anybody's a Git fan, this is a good command, you get a ordered list of ordered by the number of commits of the people. I cut it off where you were on it, Jake. There you go. Yes. Yeah. So you can, the tooling explicitly kind of understands that there's lots of individual contributors, and you can count contributions. And of course, we use functionality like that on GitHub to show, the number of commits over time. This is the all-time, I think, commit count we're seeing here, I think. But then you can put a time window on that. I'm not sure if you can see that, and doing it at the end. You can see who's committed over the last, since the beginning of 2015. I'm doing a time window there. The whole kind of tooling that people use, this is Git in this case, but Subversion and Mercurial and all the tools that version code offer something similar. You can see who's contributed to a piece of software. You can see who the authors are over a particular period in time. The other thing I think is really pretty mature certainly in open source communities is things around metrics and verification. So this is one website you can look at. There's a ton of these things. This is ranking the number of downloads that Python modules are getting here. And we can see again, I'm searching for scikit-learn here, but you can see that number of downloads it's had, I think, in maybe the last month or year. But across, on every page on GitHub for these large open source projects, they have all these build badges, or these badges that represent something. So at the end there, they deposited the software with Zenodo. They've archived a copy of it. That's pretty great. It works with Python 3.5 and 2.7. But then if we drill in on some of these Circle CI and some of these things that say build passing, then you can see, these are this I think is a code coverage project called Coveralls, which is basically measuring how well tested the project is. So there's immediate metrics available for people who are considering using the project to understand how well put together the project is. Again, here's another one linking from that page that's running the tests. Again, different tool, Travis CI now. Again, this is verifying that the functionality of the library is well tested. The other thing I think software does particularly well, and I'm not sure that these aren't pretty much the same thing, is that lots of languages now have really expressive ways of defining their dependencies, the things that they have used in their software to build theirs. And so those for me feel certainly a little bit like citations. There's a project here called libraries.io, and if we go and look at scikit-learn here, it's showing the project, a bit of stuff about the license and the homepage, but over on the right there, dependent repositories. So other open source projects that have included scikit-learn in their definition of their dependencies. There's about 2,000 of them. So for me, that certainly feels a lot like a citation, but this is a dynamic list that's built by by scanning the stuff on GitHub. And you can do this for any open source package that's managed by a package manager. So libraries does Ruby, Node, R, Python, a whole bunch. It does it for about 40 different languages, and it tries to parse out the dependency graph of all these packages. And again, I do a lot of stuff in Ruby. This is again how you would express it in Ruby. You say, literally, I'm using, these are the names of these other packages. So it just builds this graph of all these dependent pieces of software. So what if we try to copy some of these ideas? What if we try to use some of these ideas in academia? If software is something that currently is poorly credited and actually the solutions are less than ideal, well, what would it look like if we tried to incorporate some of those ideas? Put a different way, like what would it look like if we could build a better academic credit model? So this is where I expect to get eggs thrown at me with certain audiences. Like, what if we can go beyond the H-index? So does everyone know what the H-index is? I'm not even going to tell you. You're like pure because you don't know it. You'll find out one day. If you're staying in academia, I'm not going to tell you. I feel you're blessed right now. It's a horrible, horrible thing that's used by people, and it affects whether you get a job or not. And so, and the problem is right now. Say again?
The H stands for
The horrible index, yeah. And right now it's paper-centric. It's about how many papers you've published. I really don't want to tell you. This is terrible. And so, it's a paper-based metric. It's based on papers and their citations, and software, data, nothing really else factors in this score. And so what would it look like to go beyond that? Well, the first thing to say is this is a really, really hard problem. Probably it's a really, really hard problem. It's hard for reasons that kind of suck, like you're not typically allowed to mine the literature. Like I can't go and get all the papers from Elsevier that they publish because, number one, I don't have a library subscription, but even if I did, then they don't want anybody to do that because there are whole products and services built around producing these numbers that are owned by people like Elsevier and Thomson Reuters, and so these are Web of Science and Scopus, and Google is an example of that. Google Scholar is another example of that. But I think we don't talk about this because it's hard and there are like legal and technical reasons that it's difficult. And it's also a social problem. Like that we have this very, very strong convention in most academic fields that we think about citing papers and we don't think about citing much else. Things that you might want to cite. My question is, why can't you cite anything in the literature? Like if you used it to produce your research, it's relevant, right? So one idea that some of you will know who Dan Katz is. He was a program officer at the NSF for a number of years. He's now at NCSA. He came up with this idea, and I just want to use this as just one example. It might seem a little bit convoluted when I talk you through it, but I just want to talk through what a different solution might look like and why that might be attractive. He came up with this idea of transitive credit, and we wrote a little paper about how it might be a way that you could implement it. And I just want to talk you through that just for a few minutes. The idea is that, say you have a paper, and this is my paper that I've written, you basically cite anything and everything, and the idea of transitive credit is that it includes direct and indirect contributions to the paper. So let's think about what a typical set of references might look like. Well, I'm obviously going to cite myself because I wrote this paper, so self-citation is obviously my first priority. I'm going to boost my H-index, but then I'll probably cite Jones as well because their paper was good. But this is actually a cosmology thing, and I was doing some work on WMAP data, so I'm going to cite the data set. So imagine that there isn't a paper about WMAP for a minute. I'm going to cite WMAP, but I'm also going to cite the Planck data set. So orange are data sets in this. But I also used AstroPy a ton, so I'm going to cite AstroPy. And I also use scikit-learn in my research. So these are my citations. These are the things I'm citing. And then the idea of transitive credit is that every researcher you have a unit of citation to give out. So I'm going to give myself 30% of the credit. I'm going to give Jones 10%, and I'm going to spread it out. I've got a unit of citation credit that I can give out. So you just apply weightings to all these things. And of course there'll be problems with how would you get people to do this, but just roll with it for a second. But the cool thing about transitive credit is it's a property that can be extended. So who does AstroPy cite? Well, AstroPy cites white. They also cite NumPy and SciPy because those are big. So now, by proxy, I'm actually giving, by proxy, white is getting 10% of my citation credit, my citation weight, because via AstroPy, which is 20%, we've got half of that goes to white at the end there, and of course white goes on to cite their things. But basically we build this graph ourselves, and we build it, some of it's just purely papers, and that's completely fine. But others, there's other things in this graph. We build the graph and we score people, we give people, I don't know what is it, a transitive credit score, whatever it is. But going beyond this is definitely something we consider doing, but it's hard because we have no control of this metric right now. As I say, like we write our papers for journals, they go to the publishers, and then certainly in Elsevier's case, the Scopus, the tool that counts all these citations, builds the graph in the literature, is a product that's then sold back to libraries and to departments, and this metric is sold back to us, but we have no control over how it's made, which kind of upsets me. Okay, so the fourth one, and I said I was going to present some solutions. The other one is, so the last one, going beyond the H-index, is hard, but I think it's worth trying. The fourth and final one is how do we go about elevating the role of software generally in academia? And I think there's a bunch of things. I said there were individual actions. There are things we can do right now. If you're reading and reviewing a paper, ask for authors to include citation, like what software did you use? Push it back on peer during the review cycle. Like, what did you use? Why isn't it in the references? You can ask that. That's a very straightforward question. Also, include at the individual level, if you have the privilege of sitting on a tenure review committee, let's look beyond that H-index and look at things that aren't just papers. Maybe your candidates got some incredibly useful software that a whole bunch of their peers use routinely. Maybe that would account for the fact that they have fewer papers than people in the applicant pool. Take a course. Like, one of the things that I think is there's a disconnect. I talked about that competitive advantage that I think people can realize if they invest in software or send your student on one. One of the things is actually understanding how you can benefit from modern programming languages, modern workflows, version control, that kind of thing. Obviously, I'm going to say you should sell your software on GitHub. That's just a little aside. But in truth, I think we need to think about doing all the fixes. All of these, like writing software papers is a legitimate thing to do for the individual who's trying to get career credit today. Making it possible, asking your journal to make it possible to cite software, asking them why you can't, and then the more they get feedback from academics who are effectively the customer in this sense. Lots of these companies are responsive to the request of the individual. I would love to see us go beyond the H-index. I think there is a bunch of opportunities. There's actually some relatively recent laws being passed in the EU that actually make this more interesting now. That the right to if you have a journal subscription, in theory, you have a right to mine the literature now. Certainly in Europe, which I think is pretty exciting. That doesn't mean that you're not in violation of the terms of service of the journal, which is one of the reasons it's not currently possible. But that's, I don't know. The EU is pretty bullish about this stuff, and I think we can elevate the role of software by taking some immediate actions as individuals. So I will stop there. Thanks. I'll have some time if anybody has questions. Yeah.
Great thought. Thank you for your presentation. I absolutely agree with that. There was recently a new scientific journal created here at the eScience Institute. What was it called? For publishing software, actually.
It was actually created by
The Journal of Open Source Software? Was that it?
Could be, yeah. Doesn't.
Yeah, I made that. Yeah, I made that.
I claimed credit.
Yeah.
The eScience Institute.
Yeah, definitely. Yeah, but yeah.
Thank you very much. I mean, this is a good approach to push out the software out there. If only for the single reason, if you want to pick up the research from one research group, you only have the paper, and basically you have to re-implement the software they are using for the paper, just to start at the place where they left off.
Right. Yep.
There's one idea, though, which might add to your presentation, which goes back to sharing software. I mean, you could share a paper about the software directly, like the README on GitHub and so on. What you commonly have, if you create some new piece of novel software, is that you already wrote a paper about it.
Right.
Because, for example, if you invented a new machine learning algorithm, let's say that, you of course published a paper already in a good journal that talks about that algorithm.
Yep.
And your software is nothing more than just the implementation of what you scientifically did already.
Sure.
So there's one idea. What you could do right now is, if you share the software, you use an open source software license that not only allows other people to pick up your work and continue to research what you do, but also ask them if they use the software in their scientific journals. Please cite my existing paper
Yep.
that is about the algorithm, not the software itself. So
Yep.
this would perfectly fit into the existing rules.
Yeah. So there's some good examples of that. You'll sometimes see them like all caps, like citation file in a repository. I should have put that in. That's a good example. I mean, one of the things that I think is really important is that you should respect the wishes of the author. So some people really invest huge time and effort into the paper about the algorithm. I mean, algorithms are slightly different, I think, especially if that's a novel like contribution, then I think we understand what it looks like typically to publish that, I think. And so then, yes, the software is an implementation of that, but I think there's a ton of use cases where the algorithm exists already and you didn't author that, but now you've written a project that allows people to leverage that. And then I think, ideally, software papers is like one of these things that it really upsets me that they're necessary, but I also think that our primary focus today should be on the careers of individuals who are suffering because they invest their time in software, because I think it's important that they are able to. So if a software paper is the best quick fix, whether that's a paper just that you wrote quickly so you could collect up citations, or whether there is actually a real paper, a novel academic contribution, shall we say, that is yours as well. I mean, I think you just want, I think following author intent or wishes is, I think, incredibly important. And I think the citation file is a good example of that. You see that a fair amount.
Yeah, I like that idea.
Yeah.
May I do a shameless self-plug?
Sure.
Recently, Ulrika and I released such a license.
Okay.
Called Cite.me license.
Okay.
We started with the open source software license, and we want to do one for open data as well.
Okay.
Which basically is an existing license, open source software license, plus the terms that other people, when it contributes to their publications, should cite a certain paper.
Okay.
It's github.com/cite-me/OSS.
Is that, I'm sorry to get into license, I think a lot about licenses. How is that different from Creative Commons share alike, or something like that? Or CC BY, is it different from that?
Specifically tailored for researchers.
Okay.
You really put your citation into the license.
Okay.
And it covers, like, if you have a big dependency tree where it does cut off so you don't surpass the limit of required citations if you use the software,
okay.
All that stuff,
okay.
But based on a regular open source software.
Okay. All right.
Another sort of technical solution to the citation issue of specifying the citation is something called do credit. It's a project from the person developing it is Yaroslav Kolchenko, neuroscientist.
Okay.
The idea there is to inject the citation into the software itself in a way that when you run the software,
it comes up.
All the libraries have these injections. You get a list of the papers that should be cited.
Yeah, I've seen that.
Basically, the bibliography
for
that run.
Yeah. No, I mean, I think one of the things, I think as a kind of aside, if you're somebody who is interested in getting those citations, you need to make it as easy as possible for your users to do the right thing. And you see these citation files, you're injecting stuff into the runtime, into the console. I've seen that. I think you need to make it really, really, really easy. And if that means literally writing out the BibTeX entry for people, you should do that too. Don't make them work for it.
So are there some ideas about standardizing the documentation so that you can directly cite the documentation so you don't ask people to write a separate paper?
There's really strong conventions in individual languages and communities around documentation. So like the R community has this concept of like vignettes, which are effectively like mini papers inside of their projects. And the cool thing about vignettes is the package won't build. Well, it's cool as in like it's really frustrating when it doesn't work. The package doesn't build unless the vignette compiles. So like the package will fail to build if the docs don't build. So that's like a code hygiene thing, sort of taken to extremes. I've deleted vignettes before to make them install. But yeah, so there's that. GitHub has strong conventions around like readmes being like the top level documentation. As to conventions that ban different languages? Not so much. I mean, docs as a folder is a place that people expect to look, but I think there's not, I don't know, I think most communities kind of have their own kind of standard practice, and I'm not sure there's that much transfer between, yeah.
Just to quickly add to that though, I mean, if you had the choice to write a software paper that really probably nobody's actually going to read the text of, it exists as a citable unit, what they really want is to use the software
Right.
and have usable documentation.
Right.
If you were going to spend effort on one of those two things, if you had the choice, you could do both. Writing good documentation and being able to cite that is preferable to writing a kind of semi-useless software paper to just create a citable unit.
Right. Well, and so that's, so not to do too much advertising for the new journal we've been working on, but that's kind of that, in that the software paper, if you speak to people who have written software papers, the vast majority do not report that their software was improved during the peer review process. They say, oh, no, they made me improve the docs, so the docs often get improved, and maybe they argued about the results I produced, but no, they didn't. I'm not even sure they installed or looked at the software, to be honest. So therefore it raises the question, what is the purpose of a software paper? So the journal we've been working on is it's basically you write an abstract about your software, and then the peer review is about, are there good docs, are there tests, does it have an open source license? It's about, is this well documented and available software? And then if it is, then we don't judge like what you're trying to do. We just say this is well put together, and there's an abstract, and that's how.
Typically reviewers in this journal.
Say again?
Reviewers in this.
So other software authors. So we've got people like Jake, myself, people who are experienced engineers and who are experienced at kind of releasing open source code. So yeah, but I mean, yeah, I agree. It's
Can I just get one slight
Sure.
point? One other issue that I think about when I hear your talk is the issue of the durability of these links.
Yep.
So you talked about the top 5-year time frame, but if we look in the 10 or 20-year time frame for being able to do this stuff, if you'd come here and given this talk 10 or 12 years ago, you would have been talking about how SourceForge was the place to
Sure.
do this.
Sure.
And now SourceForge is kind of a spam-riddled trap.
Yeah.
And I'm not saying that's what's going to happen to GitHub in the next 10 years.
Sure.
Not.
Me too.
But looking out 20, 30 years when some of these,
Yep.
you'd still like to be able to do,
Yep.
those GitHub links may not resolve.
No, and that's a very real problem, and so that's why for the journal we've been working on, you include a reference link to GitHub, but you also you must have archived the software with a formal archiver. So Zenodo is the one we prefer, but Figshare or Dryad or Dataverse, your institutional library. It needs to be accessible as a URL, but the software needs to be saved externally to GitHub for exactly that reason. Also, you can go on GitHub today and delete all your stuff, and we're not going to stop you. There's also that problem. So I think, the other thing, so the literature publishers have this thing. There's this thing called clocks, which is so publishers deposit copies of their papers with clocks, and it's an archive that keeps copies of the papers, and it's a dark archive, as in you can't query it today, but if the journal goes bust, that's considered a release event, and they make the papers available. And there's probably 50 or 60 journals that you can go and browse on clocks archive pages. And I think something like that for software would be interesting. Some kind of end of days scenario. What happens if a meteorite lands on North America and takes out GitHub's data centers? That would be a problem for lots of. That's true. Yeah. That's a good point. That's a fair point. Sorry, you've been putting your hand up there.
Yeah, so there's a similar problem with hardware.
Right.
In that the instrumentalists in astronomy put all this effort into building instruments, and they very rarely write a paper about their particular hardware, and hopefully there'll be co-authors on the papers that do all the data analysis and integration.
In 10 years' time when the instrument's being used.
Get that credit. So have you looked at hardware at all? Or?
Not really. I think so I mean, I have friends who build instruments in astronomy, and they sort of express frustration at this. I think weirdly, maybe not weirdly, I think there is a understanding that is an issue in that community. So you can have a PhD with no papers because I was building this spectrograph, and then the building it was in caught fire and it melted, and now I don't have any papers and I won't have them. That's okay, because it's more, we have, there's other ways of working out if somebody made a good contribution. Maybe you lean more on their references, or you talk to colleagues in the past. So I think, one answer is, there is software for every piece of hardware, so the instrumentation control stuff, I think, is entirely relevant. It might be very domain specific. Somebody, think about tons of, millions and millions of lines of code written for, experiments on the LHC, and these are, open source projects, and I think, those contributions could be recognized. They're very, very hardware specific, but actually building and designing hardware, I think that's a hard problem as well. I think it's sort of equally poorly represented.
The good thing is that those skills are in such demand that you can actually get a job without
Right, yeah.
teaching.
Right.
Patent hardware.
Say again? Yeah, you can write patents as well. That's another thing, yeah. Anybody else? Questions? Sure.
You mentioned archiving software. So if I have a version of the software that I'll use 10 years from now, I can. But the other part of that problem is, let's say I wrote a piece of software for Python 4 or something like that. That's Python 5 or whatever.
Yeah.
There's no way that I can get Python or you can run the software.
Yeah.
I don't really have a question. I just
Yeah, that's like, so I have a better one for you. Well, no, there are people who care about this, right? And these are generally librarians care most about this, or people who care about archiving generally. And technically that's, people get excited about virtual machines for that kind of stuff, which is, a solution. But I think, what happens when your VMware license expires in 10 years time? This thing. You can always, there's always dependencies in there. I met somebody once who was trying to preserve, they were at the Bodleian in Oxford, and they had been given Macintosh Plus that was written, that was used, and I'm going to completely forget who the author was. Somebody a ridiculously famous author had written all their books on. And they were interested in, and there'd been an analysis of this person's text, and they'd realized that he generally used quite short words, and they realized he had a really crappy keyboard, and so they were trying to work out whether he wrote short words because he was banging hard on his keyboard and just really didn't they were trying to understand the experience and preserve the experience of the author. And so this person was worried about whether they could run this machine, and whether they'd had literally had the rug from his office and stuff, and they wanted to preserve the environment. It's a different type of environment, but for historical reasons. They were this is this gives context for this person, and and how they were writing their books. And I was just okay, that's a serious archiving problem. I don't, did they build a mock-up of their office or something? No, I think it's I think languages and computational environments are really, really tough. I mean, this is why you can get paid a fortune if you write COBOL, right? Because the most executing lines of code right now in the world are all written in COBOL, because it's all the banking stuff, and it was written 40 years ago. So if you want to go and get rich, learn how to write COBOL, because there's all these systems that are running that nobody really is using those languages anymore, but they're running and they need maintaining. And that's why I think it's Syracuse that has a very, very big program for mainframe engineers, because there's lots of companies still run mainframes, and and so there's real maintainability problems across industry. And actually, this is why Red Hat makes so much money as well. So Red Hat guarantee that any version of Red Hat that you've ever bought, if it's Red Hat Enterprise, you'll always be able to run it. Always, forever. And you pay them a lot of money for that. So if you have a Python 2.4 dependency, they'd love to talk to you, because they have a machine that will run Python 2.4, and they'll give you security patches forever and a day. That would be a sucky job to maintain those. but yeah, I mean, I think it's really hard. I don't know what the answer is. Cool.
Well, let's thank Arfon again.
All right, thanks.